right now. Strap onto your wrist a device that possesses tens of millions of times more computing power than the guidance systems that put humanity on the moon. Think about this for a second. We take a piece of raw volcanic earth, melt it at blinding temperatures, slice it thinner than human hair, and etch billions of microscopic electric pathways onto its surface, just so you can check your heart rate while sitting on the couch. But here's what nobody tells you. To build a modern smartwatch, engineers must wage a brutal, constant war against the physical world. A single speck of dust can destroy an entire production line, and a thermal variance of just half a degree can warp a chassis beyond repair. Imagine packing a vibrant OLED display, an optical blood oxygen sensor, a lithium-ion battery, a GPS antenna, and a dual-core processor into a sealed waterproof vault no thicker than a pencil. We are talking about assembly tolerances measured not in millimeters, but in microns, where the width of a single red blood cell can mean the difference between a pristine piece of wearable tech and a $100 brick of junk. Most people never think about this, but every single component inside that sleek metal casing traveled over 30,000 miles across 5 continents before arriving on your wrist. And this is where it gets truly extraordinary. Before this tiny machine ever touches your arm, it goes through a violent crucible of fire, acid, robotic assembly, and atmospheric pressure tests that would instantly crush a submarine. We are about to step inside the world's most advanced cleanrooms to reveal the hidden, mind-bending journey of how raw dirt and fire become the smartest device you own. Step through the sealed containment doors with us, because what happens to these materials next surprised even experienced engineers. Our story begins deep inside the Earth, far away from clean rooms and high-tech clean suits. To forge the high-strength casing of a premium smartwatch, mining operations extract grade 5 titanium ore from the sands of Richards Bay, South Africa, and aerospace-grade bauxite from Australia's Weipa Peninsula. Simultaneously, lithium carbonate is harvested from a vast, blinding white salt flats of the Atacama Desert in Chile, residing over 13,000 feet above sea level. This raw lithium travels over 9,000 miles across the Pacific Ocean to chemical refining plants, where it's purified to an astounding 99.99% battery-grade purity. Consider the glass protecting your watch screen. It isn't ordinary window glass. It's synthetic sapphire, grown from pure aluminum oxide powder purified to 99.999% purity. This raw powder is heated inside specialized vernal induction furnaces to a blinding 2,050 degrees Celsius, or 3,722 degrees Fahrenheit, consuming immense amounts of electrical energy. Over hundreds of continuous hours, single crystal sapphire boules slowly crystallize like frozen light. A single 300-pound sapphire crystal can cost upwards of $15,000 to cultivate, and cutting it requires industrial diamond saws spinning at thousands of revolutions per minute. Then there's the heart of the machine, the silicon. Raw quartz sand sourced from high-purity deposits in Spruce Pine, North Carolina, is refined through high-temperature reduction into electronic-grade silicon. We're talking about a purity level of 99.9999999%, often called 11 nines purity. For every million metric tons of earth mined, only a fraction of a percent makes it into the microchips that control your notifications. The supply chain logistics alone are mind-boggling, moving raw earth across 40,000 ocean miles before a single circuit is printed. But here's what nobody tells you about extracting these ultra-rare materials. The environmental footprint can be colossal if not strictly controlled. Refining 1 single kilogram of battery-grade lithium requires evaporating over 2,000 liters of native brine water, creating immense ecological pressure on sensitive desert ecosystems. Furthermore, processing rare earth elements like neodymium, vital for the tiny vibration motors inside the watch, generates tons of acidic byproduct that requires closed-loop neutralizing filtration. Engineers faced a massive dilemma. How do you build the greenest, smallest tech on Earth without destroying the environment in the process? The answer lay in advanced urban mining and closed-loop smelting operations, where up to 80% of aluminum and rare metals are now reclaimed from recycled electronics. Yet even with refined metal secured, turning raw ingots into a sleek, water-resistant watch frame presented an engineering hurdle so massive that it threatened to halt smartwatch production entirely. The transformation begins in the heavy forging shop. Solid blocks of recycled series, 7,000 aluminum or grade, 5 titanium are blasted inside multi-axis CNC machines running at terrifying 30,000 revolutions per minute. High-pressure coolant sprays continuously at 70 bar, over 1,000 psi, to blast away metallic dust and prevent heat expansion. In just 4 minutes, a solid piece of metal is carved down to a hollowed chassis accurate to within 5 microns. The air smells of cut metal and aerosolized mineral oil, while the sound of whining carbide bits creates a deafening 95 decibel roar. Next, the raw metal case enters the chemical anodization bay to receive its hard outer color and scratch resistance. The watch cases are submerged into acid tanks bath maintained at exactly 18 degrees Celsius, or 64 degrees Fahrenheit, where an electric current of 200 amperes forces an oxide layer to grow directly out of the metal itself. This isn't paint. It's a structural transformation of the metal surface that takes 25 minutes. What comes out is a sapphire hard surface that can withstand years of sweat, salt water, and friction without chipping. Meanwhile, in a Class 100 cleanroom where the air is filtered 600 times every hour, the screen assembly takes place. Ultra-thin flexible OLED panels, just 0.2 millimeters thick, are bonded to synthetic sapphire glass using liquid optically clear adhesive. A specialized UV light chamber bakes the bond at 400 millijoules per square centimeter for precisely 8 seconds. If even a single air bubble larger than 3 microns forms between the display and glass, the entire module is instantly destroyed by automated pneumatic arms. Now comes the delicate integration of the main system board, the brains of the operation. Surface mount technology machines fire microscopic surface components onto flexible circuit boards at an unbelievable speed of 80,000 components per hour. Tiny solder paste dots, weighed in milligrams, are melted inside a nitrogen reflow oven running at 245 degrees Celsius, or 473 degrees Fahrenheit, for precisely 90 seconds. The smell of rosin flux fills the exhaust lines as thousands of microscopic electrical contacts solder themselves simultaneously. Finally, the power cell and optical sensors must be sealed within the tiny frame. A custom lithium polymer battery with a high-density 4.4-volt chemistry is nested alongside the heart rate sensor array, which uses infrared and green LEDs focused through micro lenses. To make the device completely waterproof up to 50 meters, automated dispensers apply a microscopic bead of liquid silicone sealant along the rim of the case. The liquid bead is just 0.3 millimeters wide, applied at a steady velocity of 50 millimeters per second. The top and bottom halves are pressed together under 200 kilograms of force for 45 seconds to create a permanent atmospheric seal. But this tight seal creates a dangerous trapped air pressure issue inside the device. If the watch travels on an airplane, that internal pressure could shatter the screen from the inside out. And what engineers designed to prevent this catastrophe was nothing short of brilliant. To solve the atmospheric pressure problem, designers integrated a microscopic fluoropolymer membrane called Gore-Tex over the acoustic microphone ports. This membrane possesses pores that are 20,000 times smaller than a single drop of water, but 700 times larger than a molecule of air. Air can freely escape to equalize pressure, but water molecules under 5 bar pressure are completely blocked. To verify this, high-speed laser scanners scan every single assembled watch, checking for microgaps down to an unbelievable tolerance of 0.1 microns. Next comes the brutal endurance testing ground, a torture chamber for tech. Automated testing rigs simulate 5 years of extreme abuse in just 72 hours. Robotic hands slam buttons 20,000 times consecutively, while pneumatic drop towers launch watches onto solid steel blocks from 6 feet in the air. The devices are placed inside environmental shock chambers that cycle from minus 40 degrees Celsius, minus 40 degrees Fahrenheit, to plus 70 degrees Celsius or 158 degrees Fahrenheit in under 15 minutes, forcing materials to expand and contract violently. Then comes the water depth test. Watches are submerged in hyperbaric chambers filled with treated water and pressurized at 10 bar, simulating a depth of 100 meters underwater. Artificial intelligence vision systems analyze the watch face underwater, using high-speed cameras running at 1,000 frames per second to spot even the microformation of a single air bubble escaping the seal. Across the industry, high-end automated lines reject roughly 3.5% of all units at this stage, recycling them immediately to preserve raw materials. Yet despite all this advanced AI vision and ultra-precise robotics, there's one critical moment where machine intelligence fails completely and human skill takes over. Calibrating the haptic vibration motor to feel like a crisp physical tap rather than a cheap buzz requires human touch sensitivity that sensors cannot replicate. Master technicians, having trained for years, strap test units onto their wrists and evaluate vibration frequency, resonance, and tactile feedback by feel. If a unit passes the master artisan's tactile feel evaluation, it goes to the wireless testing bunker. Here, shielded inside a completely silent anechoic chamber lined with giant foam pyramids, the smartwatch fires off maximum power Bluetooth, Wi-Fi, and cellular signals across 32 distinct radio frequencies. But what engineers discovered during these radiation tests changed the global smart wearable market forever. Today, the global scale of smartwatch manufacturing is staggering. Over 180 million smartwatches are manufactured and shipped around the world every single year, generating a market value exceeding $55 billion US. China dominates final assembly, producing roughly 62% of all units, followed by Vietnam at 18%, India at 10%, South Korea at 6%, and Taiwan rounding out the top 5 at 4%. Over 350,000 technicians, engineers, and assembly specialists are employed worldwide just to keep this massive machinery turning. To put this manufacturing feat into perspective, think about this. 50 years ago, in 1976, the world's first digital LED wristwatches could barely display 4 red numbers for 2 seconds before draining their batteries. Today, a modern smartwatch houses over 5 billion transistors inside a chip smaller than a fingernail. If you stretched out all the ultra-thin copper wire used in a single day's global production of smartwatches, it would circle the entire Earth at the equator over 12 times. And here are 3 shocking facts you probably never knew. First, the gold used on internal motherboard contacts is so pure that a single metric ton of discarded smartwatch circuit boards yields 40 times more pure gold than a metric ton of raw mined gold ore. Second, the tiny speaker inside your watch actively ejects trapped water using ultra-high frequency sound waves at 165 Hz, literally blasting liquid drops off its membrane using pure acoustic kinetic energy. And third, the Sapphire glass covering premium models is so extraordinarily hard, ranking a 9 on the Mohs hardness scale right below diamond, that you could scratch it with a hardened steel drill bit and it wouldn't leave a single mark. Over the next decade, analysts predict smartwatches will evolve from simple phone companions into fully non-invasive medical diagnostics hubs, capable of monitoring blood glucose levels via continuous laser spectroscopy. Which brings us right back to the beginning of our journey. The next time you glance down at your wrist to check a text message or check your daily step count, think about the violent, incredibly precise global journey that made that fleeting moment possible. The next time you hold one of these in your hands, remember, it didn't just appear. It was born from the earth, shaped by fire, perfected by technology, and approved by the strictest standards in the world. That's not just a product. That's a masterpiece of human engineering. If you want to go deeper into the hidden world of manufacturing, tell us in the comments what product you'd like to explore next. Like this video, subscribe to the channel, and we'll see you inside the next factory.